We're continuing along with Gauss's law. Now we have the region between C and D that we're interested in. I've already drawn in my Gaussian surface, and I've started out with Gauss's law here. And Gauss's law, if you've watched the previous videos, you know this very quickly becomes the electric field is K Q in over R squared. And so the main thing we have to figure out here is what is Q in. And Q in for this heavy black dashed Gaussian surface is going to be Q on the blue sphere that I've drawn plus Q on the green conductive shell. Those are the two charged objects inside of my Gaussian surface. So it's going to be Q1 plus Q2. And Q1 is positive 6 microcoulombs, and Q2 is negative 10 microcoulombs. So some of the charge on Q2 is actually negating some of the charge on Q1, actually all of it. And we have a little bit of negative charge left over. So minus 4 microcoulombs is now our net charge. And so our electric field, K minus 4 microcoulombs over R squared. This is in the R hat direction. There's a negative sign here. This now is a negative value in the R hat direction, which means the electric field points radially inward toward the negative charge. So between A and B, we were increasing linearly. Sorry, between 0 and A. Between A and B, we were decreasing at the rate of 1 over R squared drop-off. Between B and C, it was 0. And now it jumps to some negative value and drops off as a 1 over R squared. I'm kind of guessing at the magnitudes here because I don't know the values for A, B, C, and D. But that's good enough. You get the idea from the shape here. Okay, let's go back up and see if we can do between D and E now. You shouldn't need me for that. Why don't you try to do that part on your own and see if you can get the surface charges there, and then you can turn the video back on if you need to. I've cleaned up my picture a little bit, and I've drawn a new Gaussian surface because now we're interested in the space between R equals D and R equals E. So we've got a new Gaussian surface. I've written out Gauss's law, but we know something. Now we are inside of a conductor again. So E has to equal 0. So we've got our electric field. That was the easy part. Now let's find the charge on the inner and outer surface of that conductor. So we know that E equals 0, so that means the Q in has to be equal to 0 for this Gaussian surface. And what is Q in for this Gaussian surface? It's the charge on our blue sphere plus the charge on our green inner conductor between B and C, plus the charge on the inner surface here at R equals D. All three of those added together. The charge on the sphere, plus the charge on the inner shell, plus the charge on the inner surface of the outer shell. And that all has to add up to be 0. Q in is equal to 0. So we can plug these in. We've got Q1 is negative 6 microcoulombs. Sorry, positive 6 microcoulombs. Q2 is negative 10 microcoulombs. And so we can very quickly see that we have to have positive 4 on our inner surface of that conductive shell. And on the outer surface of that conductive shell, we know that the net charge on that shell is going to be whatever charge is on the inner surface plus whatever charge is on the outer surface, because on a conductor the charge has to go to a surface. So I'm calling the inner one Q R equals D, and I'm calling the outer one Q R equals E, just because that's easier for me. And we know the net charge it was given. It was given as plus 3 microcoulombs. And we just calculated the inner surface, that's plus 4 microcoulombs. So on our outer surface, we have to have negative 1 microcoulomb. So even though this shell has a net positive charge of positive 3, positive 4 went to the inner surface, so that left negative 1 on the outer surface. Because when you add the two surfaces together, you have to get the net charge on that object. So real quickly, I'm going to jump down. I've got the charges, I've got the electric field, but I forgot to plot the electric field. So here we are between D and E. I'm going to go ahead and just draw it in there. It's 0. And then let's see if we can squeeze in the last case when we're outside of the whole thing for R greater than E. Okay, I think I'm ready to go now in my last region for R greater than E. We're outside of this entire mess now. And I've drawn in my Gaussian sphere in dashed blue line. And you have to remember these Gaussian surfaces, they are completely closed surfaces. I'm using dashed lines just so you can kind of separate them from everything else in my messy diagram here. But they are closed surfaces, and of course on my paper they appear as circles, and I may have even referred to them as circles once or twice, but they're spheres. This is a spherical charge distribution. Our Gaussian surfaces are spheres around them. Okay, so for R greater than E, Gauss's law tells us the integral of E dot dA around a closed surface is Qn over epsilon naught. And if you've watched the previous videos, you quickly get down to the electric field is equal to KQn over R squared. We can treat this as if it's one big point charge at the origin. And we just have to figure out what Qn is. We add them all up. We have these three things. We can add them all up. Q1 plus Q2 plus Q3. And their given Q1 was positive 6 microcoulombs, Q2 was negative 10 microcoulombs, and Q3 was positive 3. And so you add them all up and you get negative 1 microcoulomb. So you get the electric field is K minus 1 times 10 to the minus 6 coulombs. I guess we should put it in the right units if we're using this equation, over R squared in the R hat direction. And again, because we have a negative number now in our electric field, this is pointing radially inward. So let's go ahead and plot this real quickly. This is a negative number, so it's gonna jump out here somewhere, and then it's gonna drop off as 1 over R squared. So what I might do here, I'll just leave it. I'll just mess it up if I try to add things here. But between 0 and A, it increases linearly. Between A and B, it drops off as 1 over R squared. Between B and C, we're 0. Between C and D, it drops off as 1 over R squared, but the direction's reversed now. It points radially inward. Between D and E, it was 0 again. We're inside a conductor. And for R greater than E, again, it's radially inward, but it's dropping off as 1 over R squared. And our electric field is here. There's one other thing I wanted to point out, and that is that the conductor, there's no electric field inside of this red region, inside of that conductor. So if you're standing outside of this whole mess, where does the entire electric field come from? It comes from the outer surface of the outer conductor, this surface at R equals E. And what was the charge on that surface? It was -1 microcoulomb, which is equal to the net charge of this entire distribution. So when you're standing out here on the blue Gaussian surface looking in, you really can't see past the conductor. All you see is the surface of the conductor. But the surface of the conductor has the same charge as the net charge of this whole array. I hope that makes sense. Think about it a little bit. Okay, that's a pretty complicated setup, but I like it because it brings you through a lot of different things. It has you looking at the surface charges on these different shells. It has you looking at a conductor. It has you looking at an insulator inside of an insulator. So there's a lot going on here. Make sure you go back and digest it and understand it.